All right, let's start chapter 2 in Bio 101. So chapter 2 deals with chemistry. Now chemistry is the study of matter. And what is matter? Matter is anything that has mass and takes up space. So literally anything around us. That's what chemistry is studying. So two major aspects of chemistry. One is inorganic chemistry. That is the study of non-carbon compounds. And the other is organic chemistry, which is the study of carbon compounds. So let's take a look at the elements. Now, an element is a basic chemical substance. So this is showing sodium here. This is showing chlorine here. And so you're familiar with a lot of elements like oxygen and nitrogen, helium and hydrogen. A lot of metals like copper and silver and gold are elements as well. Now, there are 120 known elements. And of those, there's 92 naturally occurring elements. So what that means then is that some of these elements have been made in a laboratory. Now, each element has its own unique atom, all right? And so we'll get to that in a little bit on why they're unique. So one of the things that we want to show here is the chemical symbol. So you can see here, so the chemical symbol is a shorthand version of the name of an element. So it's one or two letters. And you know, if it's two letters, the first letter is capitalized and the second letter is in lowercase, like what you see here with calcium. So, you know, a lot of times it's just the first letter of the name. So oxygen is O, carbon is C, hydrogen is N, nitrogen is, so hydrogen is H, nitrogen is N, phosphorus is P, and sulfur is S. Okay? So, but, you know, why we have to use the second letter is because like in carbon, right, we already use C for carbon, so here, calcium, we use Ca for calcium because just the C is used, all right? So, and we don't want to use another capital letter because that could indicate a different element, all right? Now, sometimes we have things that don't make a whole lot of sense, like sodium here is Na. Now, Na comes from the Latin word for sodium, which is known as natrium. And so that's where that Na comes from. Another one of my favorites is lead. Lead is Pb. That comes from the Latin word plumum. So that's where that comes from. So that's where plumbing and plumbers come from. It's because all pipes used to be made out of lead at one point. All right. So 6 of these elements are what we are known as bulk elements. So a bulk element is a basic chemical substance needed in large quantities by life. And so that's carbon, hydrogen, so carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, okay, are the bulk elements, the 6 bulk elements. They make up 95% of life by mass. Now, this is showing the elements in the human body. So, you know, these elements are going to shift from organism to organism. But, you know, like calcium, that's because we have bones, that goes up a little bit higher. Potassium we use in muscle contractions and nerve activity, so that's up a little higher. Okay, so this is why you can see these things shift, but, you know, plants don't have bones, you know, they don't have nerve transmissions as well. So, you know, calcium and potassium really drop off on those guys. All right, now the rest of these elements are what are known as trace elements. And these are basic chemical substances needed in small quantities by life. So just pretty much anything else that you see here, stuff we need in our diet in order to stay alive, but just not in large amounts. Now, a compound is a substance containing 2 or more elements in a fixed ratio. So this is showing sodium chloride, which is a compound made of the element sodium and the other element chlorine. Now, the compound can have very different properties from those individual elements. So sodium is actually a pretty soft metal and is very reactive. So it, you know, you can see this guy's wearing a glove, and that's because, you know, just touch it with your skin. The water that's on your skin will react with the sodium, and you could have a small little explosion there. Chlorine is a poisonous gas to us. But when you combine sodium and chlorine together, something that can explode and something that can kill us, well, they both can kill us. But when you combine them into a compound, this creates a substance that we cannot live without, sodium chloride table salt. All right. So next, let's look at the molecular formula. So a molecular formula is a shorthand version of the name of a compound. So instead of writing out sodium chloride, we would just write, and this isn't working for me, but we would write NaCl. And if you have my notes, you could see that in there. So instead of writing out dihydrogen monoxide, which is water, we would write H2O. All right? So now let's take a look at atoms and looking at atomic structure. So this is showing an atom here. And so when we look at the atom, this is what is known as a planetary model of the atom. It's not the best representation, but it's really good at learning the basics about the parts of an atom. Okay? So planetary model. The nucleus is like the sun, and the electrons moving around are like the planets moving around the sun. All right? So this thing in the middle is called the nucleus. That is the central portion of the atom. This can contain protons, which are positively charged subatomic particles, shown here in pink, and then neutrons here, which are neutral subatomic particles, shown here in the, brownish color or whatever. And then we have electrons out here, outside of the nucleus, and electrons are negatively charged subatomic particles, and they fly around the nucleus. Okay? So this next model here is showing the electron cloud model, which is a better representation of this. So this is trying to show the electrons are right here in one plane, but the electrons move around in all different directions here, all over the place. Okay? And also, if the nucleus was actually this size, those electrons would be a football field away. So, the thing about this, we don't know exactly where those electrons are. We just know they're around there at some point. All right, so next is the atomic number. And the atomic number is the number of protons in an atom. So this indicates the element. So this is actually showing helium. Helium has 2 protons. And so what I mean by it indicates the element here is that helium has 2 protons. If we throw another proton in there, it's not going to behave like helium anymore. It's going to behave like a different element known as lithium, which has 3 protons in it. All right? So just to let you know, an electrically neutral atom has the same number of protons and electrons. So this is showing carbon. So carbon has 6 protons, 6 neutrons, and 6 electrons. And so that's electrically neutral. Another aspect that we look at with atoms is their mass number. So the mass number is the number of protons and neutrons in an atom, essentially the mass of the atom. Okay? And why we only count protons and neutrons in there is because they're so much larger than electrons, right? So protons and neutrons are roughly about the same size. An electron is 1/1800th the size of a proton. So it's much, much smaller. Its mass is negligible, is essentially what I'm saying there. Okay, so that's why we just count up those protons and neutrons. Now, not all atoms have the same number of neutrons. We can change that. So this creates what are known as isotopes. So this is an atom of the same element that has a different number of neutrons. So same number of protons, has to have the same number of protons to be of the same element. All right, but they have a different number of neutrons or a different mass number. Okay? And so this is showing carbon 12, carbon 13, carbon 14, right? And so, the number of neutrons is changing there. Now, some cases, when you have isotopes, you can have isotopes that are radioactive. So a radioactive isotope is an isotope in which the nucleus decays spontaneously, giving off particles and energy. And so that's what we see with carbon 14. So carbon 14 is actually a radioactive isotope. All right. Oh, and by the way, when you write down isotopes, you write the element and then its mass number behind the name of the element. Okay. So carbon 14 is actually made in our up in our atmosphere when nitrogen atoms interact with cosmic rays, and they convert those into carbon 14. That carbon 14 gets incorporated into carbon dioxide. That carbon dioxide is used by, so that carbon 14 gets put into carbon dioxide in our atmosphere, and then that carbon dioxide is taken up by plants. And so plants have small amounts of radioactivity in them with that carbon-14. And if you eat a plant or you eat something that ate a plant, well, you have some carbon-14 in you as well. So next is the atomic mass. So the atomic mass is the average mass of an element's naturally occurring isotopes. So, you know, we just add all these and their isotopes together, and, you know, that determines what the atomic mass is. Okay, so this is shown on a periodic table of the elements right below the name of it, or the chemical symbol. And like carbon is like 12.01 or something like that, which means the vast majority of carbon that is found is carbon-12. Actually, we have less carbon-13 than we have carbon-14. All right, so that's what we saw there. We can change the number of neutrons, still have the same element. We can also change the number of electrons and have the same element. And when we do that, we create what is known as an ion. An ion is a charged particle. It is an atom that has either gained or lost an electron. So an atom or a group of atoms. Okay? So if an atom gains an electron, that atom becomes negative. So this is shown here. So, you know, with carbon, if we have 6 protons and we gain 1 electron, we'd have 7 electrons. And so the number of negative charges in that atom would outnumber the number of positive charges. So its overall charge would be negative. Okay? So conversely, if the atom loses an electron, then the atom becomes positive. So if this carbon lost an electron, it would have 6 protons, only 5 electrons. So the number of positive charges would outnumber the number of negative charges. So its overall charge would be positive. And if you ever get confused on that, just think of this silly little joke. 2 atoms were walking down the street. And one atom looked at the other atom and said, I think I lost an electron. And the other atom says, are you positive?